Hi, my name is Paul-François, and in this tutorial I will show you how to use phievo to evolve a clock on wavefront model. So the clock on wavefront model has been proposed in 1976 by Cook and Zeman to explain how you form somates which are precursors of vertebrae. The idea is that in the tail of the embryo there is a molecular oscillator, and that this molecular oscillator is interacting with the wavefront, regressing wavefront, transforming the temporal oscillation into a spatial pattern. In 1997, Olivier Pourquier and co-workers actually identified these molecular oscillators, and today, many people in the world are actually visualizing in real time this oscillator and studying its interaction between the different signaling pathways to see how you actually form vertebrae. So in 2007, I got interested into the theoretical aspect of this problem, and with Vincent Hakim and Eric Segia, we proposed to use computational evolution to basically evolve a model, a gene network model of this process. So we use a very simple fitness function or objective function that was selecting patterns, formation of patterns in very simple gene networks, and we ended up with a very simple network here composed of an oscillator with a repressor essentially repressing itself and also repressing a bistable system. So these things came very spontaneously from the computational evolution of a pattern. We did not explicitly select for a clock, but the clock was appearing by itself. And so now I'm going to show you how to essentially reproduce this simulation using phievo. So to do that, we're going to open a terminal. And so we're first going to import the tools necessary to perform this computational evolution. So I'm going to open a Python shell. I'm going to import the software. So I have already installed the software. And then I'm going to import the necessary tool to reproduce this evolution. So these are the scripts necessary to run the evolution and to analyze the evolution. And now I'm going to download the example that is included. Oops, sorry about that. I'm going to download the different files that we need. Okay, so we're good. So now I have in my directory, I have my script run evolution to run the evolution. I have analyze run is going to be used to actually analyze the simulation. And in the directory example somite, I have all the initialization files, definition of the fitness, definition of the problem that will allow me to evolve this clock on wavefront model. And so to run a simulation, I simply run the script. And then we're good to go. The simulation is going to start in 1 second. And so this simulation is doing a very simple thing. It's simulating a growing embryo, and it selects for networks that are making a pattern. And so what do I mean by a pattern? So you see this number here, it's basically -1. So this one means that I have a gene, I have a reporter gene, and this gene defines essentially two regions or one boundary between two regions. So this is a number of boundaries between regions of high and low expression of this reporter gene. And so now what the phievo is doing is that is making a mutation selection process. It's growing the network, adding interactions, removing interactions, and the objective of the objective function, what we try to optimize is this fitness, this number of boundaries. And so for now, you still have only one boundary, and so the algorithm is going to run for a while, and then we'll see what happens. So now I'm going to fast forward the movie, let you see what happens, and we'll come back around generation 200. Okay, so we're back. So at generation 200, suddenly the fitness changed. It went from -1 to -2, basically, meaning that suddenly a new boundary appeared in the network. And then around generation 215, we went from -2 to -7 and now -8, meaning that suddenly we have many more stripes in the system. So to analyze such simulations, we have developed a Jupyter notebook to really easily visualize what happens in such runs. So what I'm going to do now, I'm going to terminate the simulation, and we're going to analyze the results. So I've just terminated the simulation, and so to analyze the result, I'm going to use a Jupyter notebook, which I'm running this way. So the commands are on the documentation. And so I'm going to click on Analyze Run. And the first thing you should do when you analyze these runs is to restart and run all cells to start the analysis. And so you have different commands that we're going to run to analyze the network. So the first thing that we're going to select the project. So it was in the directory example somite. So it has recognized it. We're going to load the project. So there is only one seed here. So we use this seed to index the simulations. Now we're going to plot the fitness as a function of number of the generations. And as I was telling you, for 200 generations, not much happened. At generation 200, you go from -1 to -2. And then around generation 216, boom, suddenly you have many boundaries appearing for the reported gene. So let's look at what happens around at the very end of the simulation to see what is the final result. So we're going to go to a late generation, say 220, maybe 224. And let's plot the topology of the network that we got. And here it is. And it's actually a very simple network. If you recall my papers from 2007, it's actually essentially the same network, where you have the input gene here, which is activating a gene that is repressing itself, and then this gene is auto-activating itself. So now let's look at what the profile, what profiles do we have from this network. So I'm going to run dynamics. And now I'm going to look at, I'm going to use these commands here. So I'm going to go at the end of the simulation and to plot the profile, to plot the pattern that is generated by the network. And so this is a profile. So here the x-axis is essentially the position along an axis that will correspond to the anterior-posterior axis in the embryo, and then you plot the concentration of different genes in the different cells. And so you see you have a very nice profile with here essentially 4 stripes. So 4 stripes, it's basically 8 boundaries, and so this is why you have the fitness of -8. So you're going up, down, up, down, up, down. And then this is essentially a model for pattern formation in such an embryo. And so now what you can do, so for instance, we could look at what happens in different cells now as a function of time. So for instance, let's focus, so let's look at cell 25 and cell 30. So let's start with cell 25. We go at cell 25, and then we can plot the dynamics as a function of time. And so as a function of time, so we have an input. The input is here to model the table of the embryo. So when the input is on, essentially, so we have the system is oscillating. And then when it dies off, well, depending on exactly when the oscillation stops, you will go to an up or down state. So here in this case, the clock stops, and then suddenly you go to up state, which corresponds to the up. This region here, which is the up value for the output one. And so now what we can do is that we can look at another cell. So for instance, let's look at cell 30. And so this is the exact same model, but then what happens that the input is basically stays for a slightly longer time. And then in this case, what happens, well, you see that you basically have one extra oscillation compared to the previous time. To the previous case, and then this extra oscillation essentially kills off the output one, and so the output one essentially stabilizes now in a low state. And so this is how you get the alternation between high and low values of output one. So this is an implementation, an evolution of a clock control model where you have a clock controlling a bistable system, very much like what we were observing in our 2007 paper. And of course, you can do many other things. For instance, you could go back, at earlier generations. So for instance, let's go at generation 207 to see exactly what kind of networks we got at this point and what this behavior is. So we can, again, plot what is this network as generation 207. And so you see it's actually a slightly more complicated network, but what we see is that basically this is probably just a bistable system. And so now if we look at the profile corresponding to this network. we will see at the very end essentially one stripe. And so now if you look at the dynamics, let's go to the last cell. We see it's basically one pulse and then it dies out. So you can play with phievo like this, evolve networks. And the SOMI case is a case that is working very well, it's very reproducible. And we provide in the package many other examples you can play with to reproduce previous results, several of our previous results. So that's it for today. I'm done with this tutorial. I hope you enjoyed it. And I invite you to download our software, phievo, which is available on GitHub. Thanks a lot.